Well, good morning, everybody. It's great to see you. I actually can't see Con Hall right now. I don't know if the video is on, Lillian, but it's just showing up as a black screen for me. So I'm actually not feeling too bad, really, but I am definitely got a bit of a sore throat, and I think I'm not in a good shape to come down and kind of spread germs on campus. So that's why I'm working from my son's bedroom today. I do have a little top hat question going, and this is what it's about, which is something it mentions in the textbook, which I think is a really good thing, which is that Newton's laws are only valid in inertial reference frames. They are not valid if your reference frame is accelerating. So, and that's what I mean by an inertial reference frame is just one that's not accelerating. So this is the question, which hopefully you can see on your top hat. If not, at least you can see it on Zoom, and you could answer it after class as soon as I post it. Oh, good. Now I can see you guys. And some of you in Con Hall. In that. Yeah, you're pinned. Okay, good. You are in a plane, and you can imagine this. You're accelerating forward on a runway. I don't know if you've ever experienced this. You sort of get pushed into the back of your seat just when you're about to take off. And some careless person has left a tennis ball on the floor. And so you see that even though the floor is flat, the ball accelerates towards the back of the plane. So as you know, from Newton's second law, acceleration is the net force divided by the mass. So there must be a force on the tennis ball pushing it towards the back of the plane, according to Newton's second law. So what is the source of this force, like the main one anyway? Is it A, air resistance? B, the plane must be at an angle, so it's rolling down. C, the inertial force. D, the normal force. Or E, Newton's law is not valid in your reference frame. And I can see from the chat window that there's a lot of frustration with Top Hat today. Some people are typing their answers into the chat window, so it's okay. Oh yeah, let's look at the Top Hat page. Good point. So this is what you're seeing, and it also gives that text thing. Let's give 60 seconds just to answer this. So again, you're looking for which of these five forces is kind of causing that tennis ball to roll towards the back of the plane. I don't know if you can discuss if you have a neighbor. Okay, 10 seconds. If you can't answer now, you can always answer it sometime after class on the weekend. Again, sorry, it's a bit glitchy today. Let's see. So there were 412 answers, a little less than usual. I wonder if it has something to do with the fact that I'm working from home. So actually 56% of you are kind of getting what I'm talking about here. It's a bit of a strange one, but basically I liked E. A lot of people actually talk about these fictitious forces. which we don't really use in this course. Like centrifugal force is going to be one that we're going to talk about later. But the idea is that from sort of the land point of view, the tennis ball is not accelerating backwards. What's happening is that the plane and you are accelerating forwards, and the tennis ball is more just trying to obey Newton's first law, that there isn't much force on it. So, and this is not a term I use in this course. Although we will talk a little bit about fictitious forces in a future chapter, but this is so E is the one I'm looking for. Okay. All right. So there was a pre-class quiz. Unfortunately, there wasn't a little survey in the pre-class quiz, but there were a couple of questions which I just want to go over because they're not so easy. But this one, the idea here is that if you've got a y-axis and an x-axis, that if you're on the bus and you're going, I guess, in the positive x direction at 35 meters per second, and you throw a coin up and down, I guess it'll trace out a kind of a parabola in, I guess, the pedestrian point of view, in which, it's starting with Vy and it's going to the right at 35 meters per second. These are the components. And then up here, Vy equals 0, but it's still going to the right at 35 meters per second. And then down here, it's going down. There's a component down, but it's still going 35 meters per second. So what happens is that V sub y changes by 9.8 meters per second, I guess negative 9.8 meters per second every second. And then, but V sub x is constant at 35 meters per second, always. And that's I guess, in the pedestrian reference frame. Vx equals 0 in the reference frame of the bus, but it does the same y motion up and down frame of bus. And in physics, both of these are valid inertial reference frames as long as the bus is going at a constant velocity. Okay. Next question was, same forces are exerted on two objects. The second object has twice the mass of the first object. So let me just go through this. I would say that A is the sum of the forces divided by the mass. The magnitudes, I guess, are also related by this. If you take off the arrows, you get A is equal to the sum of the forces divided by the mass. So the sum of the forces on 1 equals the sum of the forces on 2. They have the same outside forces, but the mass of 2 is 2 times the mass of 1. So A1 is the sum of the forces on it divided by its mass, and A2 is the sum of the forces on it divided by its mass. But what you can do is plug in, this is actually just equal to F1, so it's the same, divided by 2m1. So what this looks like is a half of A1. So A2 is equal to A1 over 2, or A1 is equal to 2A2. And that was the answer there. So you guys got that? Okay, and then the third one, which you got 100% on, is unbelievable. I think it's pretty straightforward, but basically, the force of gravity, I guess I'll call it Fg, is equal to m times g always, unless you happen to be an astronaut. So if you go off to the moon or something, then it'll lead into a different value of g. If we look at Piazza, I guess, because there's some comments on there. So I just accidentally didn't put a survey question this morning on the pre-class quiz, so I will resume that on Monday. So this is really useful. Someone said they have an issue with question 14 in chapter 2. The question says choose the statements, plural, that are not correct. but there's only one, you can only choose one on the Quarkus. So I went through and checked that carefully. You have a very good point there, but the fact is that only one of the four statements is not correct. So I think the problem will still work. We have to figure that out. And then there's the bumper car question, which I think also Aaron actually answered this in the Piazza, which was good. You have to, I think you pretty much have to assume that the bumper cars both stop after the collision. With this textbook, sometimes you have to make assumptions, and in real life, you have to make assumptions to solve things. And then, of course, Tuesday, we had this mini test. Someone was asking about, do we do it online? So it's an in-person test. It's in 255 McCall Street, which is called the Exam Center. I haven't yet assigned you to a room within EX, but there's only a couple of rooms. There's downstairs is 100, then, but you will be assigned a room probably either later today or Monday. And you'll have to check on Quarkus as to which room you go to, but I'll announce it in class on Monday for sure. I think it's going to be assigned based on your last name. But definitely that's at 6 o'clock in McCall Street. And people were asking about the age sheet, whatever a piece of paper is, the printer paper kind of thing. Also called A4, I think. Okay. And yes, it's so I saw on the thing, it's only covering chapter 2. I guess chapter 1 as well, like maybe significant bigger stuff, but and units you're gonna have, but really the questions are all coming from chapter 2 stuff, like you've been doing on the problem set 1. Okay. All right. Okay, and this is another one. Let's actually start this as a top hat question. This one you can kind of try to guess. It's one of the strategies that I have sometimes when I take a multiple choice test. Is I read the question and I then look at all 5 answers and see if, just by using simple logic, if I can rule out any of the answers and cross them off. And if I can, I think in this case, you could probably rule out 4 of the answers. And in that case, the only remaining one must be correct. And you may be able to save your self some work. And again, I can see on the chat window on Zoom, someone asked, we only have multiple choice questions for the mini test. That is correct. It's 7 multiple choice questions, actually. So that's a skill. But I have hired a human marker to mark the real term test 1 that is happening on October 10th. So that will also involve a written problem. But we'll have a lot of practice between now and then to work on written problems. So what are we asking here? Sorry. I'm going to go back to my PowerPoint, but hopefully you can see something on top hat. When I stand on a scale in my bathroom, it reads 185 pounds. Yeah, I definitely wrote this a couple of years ago, but it did read it. So, and 2.2 pounds is 9.8 newtons. So this means the upward force on my feet when I'm standing still is about 824 newtons. So that's actually what your scale reads, is it reads what the upward force is that's supporting you. So if I were, instead of my bathroom, if I were to bring that scale to an elevator and stand on it, and it's accelerating upward at 1.5 meters per second squared, then what is the force on my feet? And you can try to take a wild guess with no calculations at all. Give you a second to do that. And then I'll work it out, I guess. So let's show this answer. So once again, I think my normal, when I'm not accelerating, weight, I guess, or what it reads, the scale reads 824 newtons. So if I'm accelerating upwards at 1.5 meters per second squared, what should the scale read? Maybe 15 seconds to click in on that. Good survey says 73% of you are voting for 950 newtons, which I kind of like because all I did there is I just ruled out a lot of the other answers. So, but let's actually do it, because maybe you would be asked, what is the voice, right? So, but I think it's got to be a bit more because it's supporting you as you're accelerating now. So you have basically, if I am accelerating upward at 1.5 meters per second squared, then the net force, there must be a net force on me that's upward. So the upward force of the scale has to more than cancel the downward force of gravity. So, so by the way, mass is equal to the force divided by g. So 824 newtons divided by 9.8 tells me that my mass here is the mass. So if I'm on an elevator, let's draw a diagram here, and there's the scale, and there's me, and I define plus y is up. Then let's draw a force diagram. So the first thing is the sketch, the next thing is the force diagram. So I've got the force of the scale on me, and then I've got the force of the earth on me, which we know is 824 newtons. The sum of the forces is equal to the mass times the acceleration. The acceleration is equal to plus 1.5 meters per second squared, with up defined as up. So you just say sum of forces equals mass times acceleration. So the sum of the forces, you can read that off of the force diagram. So you've got F scale on me minus 824, and then equals mass times acceleration. So I guess it's mass is 824 divided by 9.8 times 1.5. And what am I trying to solve for? I'm just trying to solve for the scale. So I've got F scale on me equals 824 plus 824 over 9.8 times 1.5. Maybe I should actually use the calculator app here. So it's good to start getting used to using your calculator. I would say I've got 824 plus, let's open a parentheses here, 824 times 1.5 divided by 9.8 and parentheses equals, and I got 950. So that's where that's coming from. Equals 950 newtons. So it really was B. You guys okay? Okay. So Newton's third law states, so we talked about Newton's first law, which is that if an object has no external forces on it, it moves at a constant velocity in a straight line. And then almost a special case of, or that's almost a special case of Newton's second law, which is that the acceleration of an object is equal to the net force divided by its mass. Newton's third law is quite different. It says that when two objects interact, object one exerts a force on object two. Object two in turn, exerts an equal magnitude, oppositely directed force on object 1. So in this diagram, you might say that the diving board is 1 and the person is 2. So the diving board exerts a force of 1 on 2. Well, the person also is pushing backwards on the diving board, 2 on 1. And Newton's third law states that those two forces are equal and opposite. Note that these forces are exerted on different objects and cannot be added to find the sum of the forces exerted on one object, I guess. So what we're saying here is that forces always come in pairs. Every force in interaction involves two objects and two forces. These forces are equal in strength and opposite in direction, and they are always the same kind of force. So, like if I push against a wall or something, or my hand, I've got the normal force is one force. The equal and opposite force of that pair is also a normal force. Or if there's friction, then both equal and opposite forces will both be friction. And they always act on different objects. 1 on 2, 2 on 1. Okay. And then this is the do you believe it? So think about this. You've got a truck pushing a car up the incline with a constant forward acceleration. So they're both accelerating up the hill. And maybe there's an incline, a theta. And the car and the truck are in contact during this acceleration. So what I'm saying is that the force of the truck on the car is equal to the backwards force of the car on the truck. All right. And if you don't believe that, let's try to zoom in and imagine that there's a spring between the truck and the car. And what I would say is that this spring doesn't know what side is what. It doesn't know that there's a great big strong truck on one side and a broken car on the other side. It's just compressed, and from its point of view, it's symmetric. So I would say it must push with an equal force on either side, sort of by a symmetry argument or something. That's sort of, if you kind of get that, that's sort of the crux of Newton's third law here. Let's do a top-hat question on this. Let's start this. It's about a Mack truck. So I'm going to go back to the display for a second. This one. So this is like a versus. So what you imagine is that there's a guy in a Mack truck driving north on a highway, and meanwhile there's a mosquito flying south on the same highway. And so the question is like, and they're destined for a head-on collision. So when they collide, is the force of the Mack truck on the mosquito greater than, less than, or the same as the force of the mosquito on the Mack truck? Discuss with your neighbor, see if you believe it. "40 seconds for that." I will say that on my Zoom chat, Natalie asked a very good question about the car and truck accelerating up the hill. The question is, if the forces are equal and opposite, what causes the acceleration? So that's a really good question, which I'll get back to after we do these two top-hat questions. I promise I'll answer that. 20 seconds. And I got a follow-up question to this one. 5 seconds. Okay. So what you guys say? Okay. Okay, you're definitely playing along. I think 14% of you, I kind of get what you're saying there. What I'm going to do is give you another question, which looks almost identical, but it's slightly different. It's asking, so a Mack truck drives north on the highway, collides head-on with a mosquito. Which of the following is largest? The damage the Mack truck does to the mosquito, the damage the mosquito does to the Mack truck, or both of these are about equal? Yeah, people are asking if damage and force. So a little bit more time, but yeah, basically think of it from the Mack truck's point of view versus the mosquito's point of view. Priya said the mosquito isn't going to be alive to have emotional damage. I guess I'm just talking about physical damage here. This chat is hilarious. Okay. Yep. So I see some good questions. Let's discuss this one quickly. Just see what people answered. Yeah, the damage the Mack truck does to the mosquito. So I totally agree with that. I think if you were to, sue for damages, for example, you got all the future earnings of that mosquito because the mosquito's dead, right? So he's quite damaged. He's completely splattered on the windshield. Whereas if you think of the Mack truck, he might have a coffee and it's didn't even jiggle. Okay, so there's no damage at all to the Mack truck. So what's going on here? What I'm saying is that the acceleration is it's sort of what happens here. The force is equal on the truck and the mosquito, but the acceleration is not equal. So the acceleration, remember, is higher if mass is lower. So you get equal forces, and you divide by the mass. So if you divide by the mass of the truck, this tiny little force, then the truck doesn't accelerate at all, so it doesn't jiggle. So, but if you divide by the mass of a tiny little mosquito, in whatever micrograms or something, you get a huge acceleration, and so it receives more damage, I think. Okay. And then, so someone was asking actually a really good question. I think it was Natalie, which is about this, going back to, remember this truck. Natalie was asking, well, then why do they accelerate if the forces are equal and opposite? So that's a great question. What's happening actually is that there's an external force of friction from the road on the truck pushing in the forward direction up the hill. Okay, so, and that is the real reason that these two objects accelerate. The forces, the internal forces they have on each other, I guess, yeah, if you're the car, then you're feeling an external force from the truck behind you. But the truck, which feels a backward force from the car, will feel a greater force from the friction on the road in the forward direction, and that's what accelerates the truck. So, and if we go, just looking forward, where are we here? Yeah, this one. The farmer has a donkey. I talked about this last time, and the idea is that if the donkey pulls forward on the cart, by Newton's third law, the cart pulls backward on the donkey with an equal and opposite force. So the donkey says to himself, well, what's the point? I'm never going to pull this wagon again. So the donkey's reasoning is that Professor Harlow says, according to Newton's third law, if I exert a forward force on the wagon will exert an equal magnitude force backwards on me. Well, that first sentence is correct. The wagon really does pull backward on the donkey with the same force that the donkey pulls forward on the wagon. So then the donkey says, so I give up. I'm never going to accelerate the wagon. That's where the donkey's flaw in the reasoning is. So forces, so I guess they're thinking that the force would cancel on each other, but forces cannot cancel on each other if they're acting on different objects. And what really solves this, it's the same with the truck going up the hill. There is a third object here, which is the ground. The forward static friction on the donkey's feet from the ground is larger than the backward rolling friction on the wheels of the wagon. So if you take a system to be the donkey and the wagon, there'll be a forward net force on that coming from the ground, provided by the earth, I guess. And that is why they can both accelerate together. So this Newton's third law, it really only applies in certain special cases. It can be very useful in certain problems, but don't get too mixed up by it. Remember, you've got two different objects, sort of two different force diagrams, and these pairs of forces are equal and opposite on different diagrams. Yeah, what's the forward static friction? We haven't really dealt with friction yet, but you can imagine, I guess, that the feet of the donkey don't want to slip backwards because they're kind of sticky on the ground, and that gives you a forward friction force. Makes sense. I'm seeing some good questions on the chat here. Okay. So let's talk about these interaction pairs. And this is kind of a cool one. So consider it an accelerating car. You step on the gas and the car accelerates forwards. The question is, why does your car accelerate forwards? Well, in physics, what we would say is that, first of all, your engine provides a torque on maybe the back wheels, which rotates the back wheel counterclockwise in this direction, actually accelerates that in the counterclockwise direction. Then what happens is that the tires of the car push backward on the earth. And we're going to talk about this more, but that is actually a static friction force. It's two surfaces that are parallel. It's the tire and the road, and the tire kind of wants to push backwards, and so it pushes the road backwards. And then what happens is there's an equal and opposite force against static friction of the road pushing forward on the car, and that is what propels the car. It's this force. Bet you didn't know that, did you? It's friction which makes your car go. But you do know that if you're from Canada and the road is all icy in the winter and you step on the gas, guess what? It doesn't matter how good of an engine you have, you're not going forward without friction, right? Your tires just go and spin around. Rocket gas pressure interaction. So consider a rocket that's accelerating upward. The way this works is that first the rocket pushes downward on the expelled gas. It's actually the exhaust from the explosion that's happening there. And then, in turn, by Newton's third law, the expelled gas pushes upward on the rocket. So the nice thing about this force is that it even works when you're not on Earth. If you're way out in space somewhere and you have some fuel and you set it on fire and you expel all the exhaust in one direction, that exhaust will provide a force on your rocket in the opposite direction that propels you. So that's a good thing. All right. So I got one more. I guess I promise I'll go back to that truck pushing the car up the hill, because that's another good one. But let's do another top hat question. Nope. People doing it. Let me actually show it on the PowerPoint first. Consider a basketball that's in free fall, and it's drawn there. And there's a red arrow, which is showing gravity that pulls the ball down. So what's the other force in this interaction? And remember, when you have an interaction pair, as it's called in your book, then the magnitudes are equal and opposite. Why don't you discuss that a little? Okay. 15 seconds to answer this one. We'll discuss. So we're looking for the equal and opposite force of gravity pulls the ball down. This was a really weird one. And the idea is that the equal and the force that has to be equal and opposite here is the gravity of the ball pulls the earth upward. So what the heck? This was kind of a strange question. So I think this is an example of one of those times where Newton's third law, yeah, there's a pizza on my head, is a little useless. So you've got this force and there's the earth. Somehow what I'm saying here is that if the earth pulls the basketball downward, the basketball must be pulling the earth upward with an equal and opposite force. But similar to the mosquito and the Mack truck, there's a difference in the inertial masses of the two objects. The forces are the same, but the inertial masses are different. So, and I can write those out. Let's say it's maybe half a kilogram or so. 500 grams is the mass of the basketball. Well, in that case, 4.9 newtons is the magnitude of that gravity force. And if you divide that by 0.5 kilograms, then you would find that you get 9.8 meters per second squared as the acceleration of the basketball. But if you want to do the acceleration of the Earth, it's also being pulled upward with 4.9. So in that, this and this are equal by Newton's third law. Okay. And then I divide by the mass of the Earth. 4.9 divided by 6 times 10 to the 24 kilograms. And then that number is equal to, I think I did that, it's 8 times 10 to the minus 25 meters per second squared. So I don't know what 8 times 10 to the minus 25 meters per second squared is, but it's basically 0. You could never measure it because it's so small. So the Earth pulls downward on the ball pulls upward on the Earth, but the Earth doesn't accelerate, and so the Earth doesn't feel it. It sort of just absorbs all that force. And that's going to be sort of the similar thing with the mosquito and the Mack truck. Now let's go back to this. What I want to do here is draw force diagrams for the truck and the car. So let's do the truck here on this side. And since this is a different object, we'll put the car over on this side. And we'll just draw a dot and a dot. And what we'll try to do is think of all the forces that are acting on this object. So first of all, there's going to be the force of gravity. Force of gravity of the Earth on the truck. And maybe the force of gravity of the Earth on the car is a little less because the car is probably less massive than the truck. What else can we draw? We can also draw the normal force, which is going to be at an angle. The force, I guess, normal of the surface on the truck, and the force normal of the surface on the car. And then what else? Well, there will be a force of the truck on the car pushing it forwards. Force of the truck. Hey, we should put maybe little arrows on these to remind us that they're vectors, right? Force of the truck on the car. Well, there will be a backwards force of the car and the truck. And what I'm going to do is I'm just going to kind of try to remind ourselves that the magnitudes of these are the same by Newton's third law, interaction pair. So these are equal magnitude. So if you're going to analyze this situation and write down equations, you can use that trick that those two forces are the same number of newtons. That's helpful sometimes, but we're missing some forces here. What we need is this is a weird one, is that there's a forward friction force. The force of friction of the surface on the truck. And the way I kind of remember that, I guess what this means is that this is normal. And S, let's put it here. S is the surface. So when I write S, I mean surface. When I write T, I mean truck. And when I write E, I mean earth. The center of the earth somewhere down there. Okay. So there's and then this little f this is friction. There must be an external forward force of friction on the truck, making it go forwards. And then there'll be a small force of friction, probably making the car go in the opposite direction. Friction on car. The car is dead, presumably, and so it's not pushing itself up the hill. It's getting pushed by the truck. And so when your engine is dead and you're getting pushed up the hill, then any friction on your wheels will be kind of in the backward direction, sort of dragging you. But if your car is on and you're torquing those wheels and those wheels are trying to slip backwards, but they're not slipping, then you've got a forward propulsion force. So that's the idea. And again, I'm going to go over this a lot more in future lectures, but this is the force that accelerates the system. So that's hopefully kind of an answer to Natalie's question on the chat there. And yeah, you'd think that the friction would be backwards in the truck, but it isn't. It's going to be forward. And I tend to think of that as if it was a slippery surface, the truck would kind of slide backwards. So whatever is countering that is going to be this forward friction. Okay. All right. I think that That's pretty much it for me. I really appreciate you guys watching me on Zoom. I hope you have a great weekend. I'm going to go get some sleep. Let me give you this, though. After having been thrown upward, a 100-gram tennis ball falls back into your hand and you catch it. So while you're catching it, is the force that you exert on the tennis ball more than, less than, or the same as the force that you exert on the tennis ball when you're holding it at rest? So think about that acceleration there. And like I say, I hope to see you actually in Con Hall on Monday morning, and then definitely on the test on Tuesday evening. So take care, and bye for now.